Welcome to the Matterhackers podcast. I'm Dave, and I'm excited to bring you guys on this journey to dive deeper into digital and additive manufacturing. Today we'll be sitting down with industry experts to talk about PLA, polylactic acid, 3D printing's unsung hero, about why it exists in the first place, its roots in 3D printing, and finally, how to succeed and what are the best applications. At this point, PLA is the material everyone begins their digital manufacturing journey with, but that's not always been the case. PLA is a breath of fresh air for anyone who began their journey a decade ago. Struggles with ABS and other commonly used petroleum-based products were alleviated when PLA came onto the scene. Its low melting point and high rigidity make it perfect for printing and understanding the mechanics of FFF 3D printing. PLA, I'd vote it the MVP of all 3D printing materials, but it gets a bad rap for some of its mechanical characteristics. Too brittle, can't handle the heat, or is known just as a beginner's material. And while all of those may have some truth, the utility of this material has shown to outweigh, by a long shot, any of those. It is the most commonly used desktop 3D printing material. On top of that, Matterhackers' own Pro Series Tough PLA shows the results of progress that is being made to advance this material in a number of ways, increase strength and durability, while maintaining ease of printing that PLA is known for. And scientists like Dan Sawyer and his team at NatureWorks are the ones leading the way.
Hi, I'm Dan Sawyer from NatureWorks, and I'm a business development leader. I've come to NatureWorks with a background in engineering, but worked, say, the first 10 years of my career in the technical side, helping customers use our material. And then the last 15 years, I've been more on the commercial side and most recently doing business development with a focus on 3D printing.
So we're here, we're going to talk with Dan from NatureWorks and all about PLA, where PLA came from, how it matured to getting into the 3D printing and additive manufacturing market. And I think you've got a ton of history here that a lot of people within 3D printing, whether it's makers or engineers or manufacturers, are a little bit unaware of. So I'd love to uncover that stone and understand how PLA became this ginormous thing that dominates 3D printing right now, and how it interestingly migrated its way there, because it's not an ordinary and highly used thermoplastic on a day-to-day basis, but it's the number one go-to for everything additive manufacturing. So
Dave, NatureWorks is a company that really is all about sustainability. And so we're based in Minnesota as a headquarters. We manufacture in Blair, Nebraska, and we manufacture plastic ultimately out of greenhouse gases. So really focused on renewability and sustainability as a whole. About 150 to 160 employees worldwide, and working in a variety of roles, a bunch in manufacturing, but also some in R&D and administration. Some of us on the, you might call it the dark side, in sales and marketing around the world.
I love that it's all made in America, like PLA in its roots are made in America, and that's a really interesting story. How are these materials developed and manufactured?
We source from greenhouse gases, and that it sounds really outer space-like, but it is the reality. It's really about making long chains of carbon and hydrogen, and so we're sourcing those carbons for the chain from greenhouse gases in the atmosphere, and we take a lot of credit for what nature does. So nature is grabbing those out of the atmosphere in the form of plants, and through photosynthesis. I think we all at least managed to get through biology in high school. So photosynthesis is the process where we're grabbing those out of the atmosphere. And so we're manufacturing today from corn sugar in the US. It really doesn't matter what type of sugar. It's the fermentation process, much like a lot of us who like fermentation in their beverages. It's really a sugar source through a fermentation process to produce lactic acid, the starting material for making PLA. And so it's really about whatever sugar source is abundant and plentiful where you're manufacturing. And so with a manufacturing operation in Blair, Nebraska, just north of Omaha, corn sugar is the most plentiful, abundant source of capturing that carbon locally.
Yeah, and I love that story, because if you were to move to a different geographical region, you could use other sources for this, right?
Yeah, absolutely. So lactic acid is produced around the world for a number of different applications, PLA being one of them. But in Asia, it's sourced from sugar cane. In Europe, lactic acid is produced from beet sugar. So really any of those, whatever is abundant and plentiful in the area. We've even looked at cellulosic feedstocks as a future option. Not there today, but it's really about how do you get the carbon that you need to put together in the polymer chain, and having a good source for that fermentation process.
When you talk about these long polymer chains that are based off lactic acid that get turned into PLA, like the manufacturing method is, I mean, just to kind of state the obvious, and maybe you can go into it a little bit deeper, is drastically different than other polymers that people are using. Nylons, ABSs, PETGs, those are like ordinary, both highly manufactured for daily goods and really used in 3D printing, right?
Yeah, and our material gets used in a lot of applications as well, and some that are very much sort of those commodity products, if you will.
I love that it's like a beneficial carbon footprint when you use PLA, as well as all these tangible places that I've run into it personally, including diapers and tea bags and, those clear plastic cups that you get at concerts, things like that are the last places outside of 3D printing that I might have interacted with it. But how did NatureWorks get involved into 3D printing? What was your first experience in 3D printing, and how did that perpetuate into where you are in the market today?
I was looking at emerging businesses for us, and an opportunity came to us, and people were interested in getting some material for 3D filament, and I had to look up what it meant, and it was some of the early filament converters out there, and looked up what they were doing, and I actually got contacted by one of the early printer manufacturers. Someone out of Brooklyn had contacted me and was interested in getting material, and we're looking for opportunities to move a rail car in and fill it up with plastic and ship it out. And so I said, well, when could you use 1,500 pounds of resin in a box? And a very perplexed person on the other end said, well, maybe over the course of a year we might get through that amount of material. And it's interesting, the same company is probably consuming a truckload of resin almost on a monthly basis. Probably on average they are right now, a whole truckload of resin, so about 40,000 pounds a month. So to be honest, early on I missed it. As person responsible for emerging businesses, I thought, man, this is one for some of our distributors in the resin space to take some of our resin and spread it out and serve these opportunities on a small basis. And so I steered some of the companies that way, to be honest. And the more we looked at it, we had heard of additive manufacturing and 3D printing. Being in Minnesota, Stratasys is just down the road, and so we had met them through some of the plastics industry association things, and we really thought, hey, if there's an opportunity for us, it's going to be with those big industrial producers. Well, what we missed was that the material, it turns out, really worked pretty well and didn't require quite as much engineering in the equipment, as tight of controls in the equipment to make it work. And so we started to realize that as people were asking more and more for material, and we're using it, and some of the early industrial patents expired, and the desktop machines started coming out and becoming more common. And everything we heard was your material, PLA or NGO is our brand name, really is the material that works the best on these systems, and it tends not to warp. It doesn't smell as bad as materials like ABS, and so it's just easier to print with, and we don't need a heated chamber was an early question that got asked a lot, and so it just more and more became the go-to material for desktop 3D printing as that market took off.
When you got feedback from the market, what were they saying? We're saying obviously that it was working, but like why was it advantageous versus other materials, and what was their plan with it moving forward?
Yeah, I think like us, a lot of the early users were interested because they had a little bit of a sustainability mindset. And so that's what attracted them more than they were saying, well, we think we're going to grow this business. We're going to use more and more material. We want something that's more sustainable. And as they started to print, it was really that it stuck to the bed better than they were used to. It was that it didn't warp like ABS did if you didn't have a really tight temperature control around the printer. And so, and the smell was a big one. As people were using them in a non-industrial setting, they wanted something that didn't stink, and so those were some of the early pieces of, I would say, performance feedback. We hear it over and over. Everybody is interested in the sustainability angle, but the best opportunities for us are where we bring some performance, and the sustainability is more kind of a nice to have than the main thing that people are buying for.
NatureWorks has brought to market this kind of magical material. Anyone's first print, almost 95% of the time, I bet, is PLA.
Yeah, and I think you hit on some good things. One, I would talk a little bit about how the material melts and flows, so it's a good fit there. The fact that through the control of the chemistry, we can go from something on one end that can crystallize reasonably fast, it's not the fastest crystallizing material, to something that's completely amorphous on the other end, and we can control in between there depending on the application. And that can allow you pretty unique melting behavior, the ability to make something that is more heat resistant, but also it melts and flows and sticks together layer to layer. But it is a strong polymer. Probably the only knock that we heard early on was it tends to be a little bit brittle, and that's it's inherently it is kind of a stiff polymer. Luckily, in looking at some of the other application areas that we were working on, we knew some tricks that we could use, modifying the polymer with additives, taking advantage of that chemistry and having faster crystallizing resins to sort of overcome some of those challenges around heat or toughness of the material impact. And with the toughness, we kind of talk about two. One, where a lot of companies have added a little bit of additive into their filament to make it easier to process. But on the other end, we've really impact modified with some of our grades that we've developed specifically for 3D. Around 2015, we really started focusing on developing grades specific for 3D, and we were able to take advantage of what we really struggled with in some of the other areas like injection molding in improving the properties, and inherently was easier to use some of those tricks we learned there in 3D printing than it was in injection molding, actually.
Yeah, and I love to hear that NatureWorks is taking the success in the additive market that you've had, running that back through product development. So NatureWorks' major product is NGO, and within NGO, you guys are really doing a lot of product development and performance enhancements to meet, some of the weaknesses of PLA. Weaknesses just being a term of like, why might you not use PLA, and bringing to market new materials. Can you talk a little bit about the product development cycle that you're doing or have been doing over the last 5 years, and specifically some of the grades that are currently being used in 3D printing?
So the first grade that we launched was our 3D 850, and with that, it's a grade that could crystallize more rapidly. So crystallizing, you basically, it's like making something more like an ice cube, where it's crystalline form, and you have to heat it up enough for it to melt before it will really flow and soften. So that's a good means or a good lever to address heat resistance. So the first grade was developed to allow people to anneal and be able to crystallize. We found that when you use that particular grade, if people had their own formulations improving the impact, that they would see a bigger bump with that grade than they did with kind of our standard packaging grade that had been used most often in 3D printing. And so the 3D 850 we started to sell initially, but at the same time we were already working on, all right, not everyone's going to have access to compounding themselves and have the additive knowledge that we've developed over many years. So we developed, at the same time we were working on developing a grade where we modified it ourselves for those that didn't have that skill set. So use the same 3D 850 as a base, but added impact modification and sped up the crystallization further. And that's when we launched the 3D870. And I think that's when you and I, Dave, first kind of connected, and you were interested in learning, what are these different grades? What do they mean? And so we sat down and chatted through that.
Yeah, that was just as, the 3D870 was launching. We came to market using that base material for the Pro Series Tough PLA, which is, in terms of my own usage at home and things, it's as easy to print as any ordinary other PLA, but you have this huge benefit of it's got some impact modifiers in there, so it is a little bit more robust, not as brittle, but literally just as easy to print.
Yeah, that was definitely our goal. We knew we couldn't lose that printability. That was the reason people were attracted to our material in the first place. And so keeping that base, but adding the toughness. And we see, Kyle, we've measured stuff that had impact in a 3D printed part, impact that was almost on par with injection molded versions of ABS.
What's next for NatureWorks and I guess the materials and some of the product development, or the growth of the market, which I'm sure as infant as it was 8 years ago, it's exceeding expectations, or like where's the market in terms of how you guys see it in your portfolio?
Interesting. Couple things from a market standpoint. I'd say, Dave, we really built the base on consumer or desktop printer market, maker space, and eventually we're seeing that line kind of migrate into more and more professional or industrial settings where people are finding ways to use it. The COVID response, you guys did a fabulous job enabling the response with PPE printing out there, is just a good example of where this technology, even in a desktop printer, as long as it's a decent one, can be used in an industrial setting and provide just-in-time manufacturing. So with the 3D870, we were trying to get more of those engineering-like properties that will fit, and things like jigs and fixtures used in manufacturing. And so not going away from the maker space and desktop printing for cool, neat things that people can print, but also adding some more practically relevant prints that are used in industry. We think printers that are printing for professional applications are going to print day in and day out, and those performance properties will be more and more important. So tailoring the resin to fit some of those. We're starting to look at large format printing, where that less tendency to warp than other materials can really play out. Imagine if you're trying to print a 30-foot long print in a super large format printer, any little bit of warping and you're going to pull off the print bed. And so we're trying to make sure we even tailor some resins for those even higher demanding applications. Things like layup tooling for thermoset composites, or precast concrete forming. Some of those real large format applications are an area that we find really interesting going forward.
Anything else that you wanted to cover, Dan?
Yeah, I'd mentioned, looping back to the whole sustainability, I think we really focused for a number of years on making sure the product performed in the application and was meeting the needs of the applications. And we're still doing that for sure. But we're really kind of going back and revisiting how we fit into what we talk about as a circular economy mindset, and trying to tackle questions about after use. What do you do with the material after use, and what do those environmental benefits mean? So being based on a sustainable material, sustainable agriculture used in manufacturing the feedstock really means that every pound or every kilo spool you use, you're going to have less impact than a fossil-based material. But we're starting to look at next life or afterlife, and what do we do with the material, whether it be recycling traditionally, mechanically, or chemical recycling as another option. Really starting to work on that. A misconception I'd like to quickly talk about is sometimes people say, describe that we make a bio-based or a renewable-based polymer, and people will say, so it's biodegradable. And usually now that I've been through that 50 or 100 times, I play devil's advocate and say, well, what do you mean? and usually that's where they freeze up. And so compostability is a value proposition, and it's relevant in some of our businesses, the tea bags or coffee capsules that we're working on. It's food serviceware that you see in big venues, because that allows food waste to go to a compost site rather than landfill, not having to separate the two. In 3D printing, the beauty of this market is that you can print whatever you want, and that oftentimes means it's a thick part, and you're not going to be able to get that certified as compostable. So really trying to educate the market.
The entire life cycle of PLA, from where the material is derived from to what you can do with it after you're finished with it. The power of PLA is its entire life cycle is conscientious of that. If somebody wanted to find out more about NatureWorks or NGO Plastics, where would they go?
Yeah, really going to our website. We keep that as up to date as possible. We have a newsletter like you. We put out stuff on social media on our channel. So our website is probably the first place to go, natureworksllc.com, and then following us on the newsletter and so.
Thank you so much for your time. I think learning a little bit more about PLA is right in, you guys are riding the market, riding a growing 3D printing market, and hopefully it's becoming a more significant part of your business, so that it's something that NatureWorks can focus on to just continue to improve the capabilities of 3D printing itself. And I really appreciate your time.
Yeah, thanks for interviewing me, Dave. It's always a pleasure working with you guys, and appreciate what you guys are all doing to build the market and connect with the users out there.
Thanks, Dan.
Now that we've learned a little bit more about PLA, how it's manufactured, how it began in 3D printing, and how it's used in general, let's work on demystifying a little bit. How to succeed with the material itself when you're 3D printing with it. And for that, we'll talk to our own Taylor Landry.
I'm Taylor Landry, Director of Research and Development at Matterhackers.
Hey Taylor, we're talking PLA. When you think PLA, what are like the first 20 words that come to mind when you think of PLA, where it's used, and how people are using it?
PLA is easy to deal with, easy to print with. It's the thing that we recommend most for beginners. It's cheap and relatively strong given everything else.
I think that's one of the biggest things to demystify, actually, is its utility. When you say strong, if I've heard that it's a beginner's material and it's no good for some serious applications, what are some of the data that you may use to offset those statements?
So there's obviously different kinds of strength, and tensile strength, flexural strength, compressive strength, all those things. So depending on the way that you're planning to use it, it may or may not be strong in the way you're looking for it. But just in general, it's really stiff, which is good for a lot of applications. It has really high tensile strength, also good for a lot of applications. So in general, compared to most other filaments, it's actually stiffer and has a higher tensile. So in those ways, it is not weaker or less than other materials.
And what are some of the watch out applications?
So anything that has high or repeated impacts is not going to be good for PLA. It has very poor impact resistance in general. And I'm talking regular PLA here. And anything that's going to be exposed to elevated temperatures, and really anything that would be equivalent to a hot car temperature-wise is not going to be ideal. And then direct sunlight obviously is also in that bucket. But other than that, I think it can be used for a wide range of things, not just because it's easy to print with, but because it is actually strong and functional.
And we just spoke with Dan Sawyer from NatureWorks, but how come PLA became such a widespread material and used in 3D printing? What are its specific properties that made it highly utilized?
Well, early on, the biggest thing is the print temperature. So it doesn't have a high heat resistance, but part of that is it is able to be extruded at a much lower temperature than a lot of other materials. So we didn't used to have all metal hot ends and all this. We were limited by the materials we could use for the hot ends. And so we were capped around 240C. Printers in general couldn't really print above 240C. Well, PLA doesn't need to be that hot. It needs, 190 to 200 will work for most PLAs. So that alone is probably the reason it floated to the top back in the early days. But couple that with the fact that it's cheap, it doesn't smell bad. It actually smells like baked cookies for a lot of people.
A little sweet.
It's sustainable and all of that good stuff with the corn-based, the bio resin, which I'm sure Dan talked about. But it's non-toxic. You could eat it and not be in trouble. I think those are all probably reasons why it became popular at the beginning.
So I want to step back a little bit from application and some history, and instead focus on, you've spent the better part of 5, 6, 7 years even answering phones and emails here at Matterhackers of people having issues with PLA. And it's a super easy material to use, but maybe just lay out the best getting started guidelines for how to succeed with PLA when it comes to bed surfaces, print temperatures, slight settings, in a real consolidated way. What's the best practice for someone to succeed with the material?
Yeah, I think the part of the reason there's some confusion with PLA when you're starting out is because it's so easy to deal with. There are a lot of different ways to make it succeed, and those kind of get blended together. So, for example, you can print it without a heated bed on blue painter's tape, and it'll work just fine.
The OG method.
Yeah, you can also print it on a heated glass plate with nothing on it. But if you try to print it on a heated glass plate that has blue painter's tape on it, you probably will have some issues with curling or the tape peeling up. So you can't blend those methods. So part of it is just understanding what you have, what you're starting with. But PLA will stick to almost any build surface that's out there, whether it's plain glass with nothing, hairspray, glue stick, blue painter's tape, build tack, the the powder coated PEI sheets, you name it, it'll probably stick to it. So the first thing is just knowing what you have on your printer and looking for the appropriate methods to match that.
And we've heard printing on glass plates that are heated is kind of the ultimate goal to get clean surfaces. That's sort of shifted over time with textured PEI, but what's your go-to build surface?
Yeah, I think that's going to be ultimately dependent on what your goals are. If you want a glossy, shiny finish, nothing beats straight glass with nothing on it. A lot of the issues with surface quality on that first layer came because people were adding glue stick or hairspray or some other adhesive to the glass, which then takes away that smooth, shiny surface. Something like build tack came in and doesn't require any adhesive. It doesn't give you the same shiny surface as glass does, but it's uniform and smooth and really nice looking. And now the powder coated sheets, which have come in the last year or two, they essentially give you a textured surface so that you can hide impurity or imperfections and issues with that first layer if that's what you're going for.
If we go to the next step of print temperatures and extrusion speeds, you're cracking open a brand new unknown roll of PLA. Where do you start and why do you modify temperatures or extrusion speeds?
So the main thing with PLA is it likes to be cool, meaning there really is no such thing as too much cooling on PLA in general. And a lot of the issues that people have are due to inadequate cooling. So the first thing to understand is are you in a hot environment? Do you have a hot printer? And by that I mean 200 degrees on your printer may be different than 200 degrees on another printer. So understanding those variables is important. And if you don't know any of those things, then starting at the lowest temperature on the recommendation from the filament is what I would recommend. So a lot of filaments, that's around 190 C. And just extruding some in the air from there. And you can judge a lot. If you're not hot enough, the filament's generally going to look pretty dull or a matte finish. And as you increase the temperature, you'll get more shine or gloss to it. And so there's kind of a happy medium in there. Obviously too hot's bad, but you just be bumping up the temperature a little bit until you get a more shiny, glossy filament that's coming out.
So essentially you want as low of a temperature to succeed with consistent flow and extrusion.
Right.
Okay. In terms of like finishing, I know there's been a bunch of questions that have been asked of how to glue parts together, what should I use to finish them, sanding, stuff like that, if someone wants to make it look prettier. What are your recommendations there?
So because of the low heat resistance of PLA, regular sanding can be a little problematic because when you're sanding, you're generating heat. And so if you were to get a belt sander out or something, what you end up doing is melting the filament more than sanding it away. But that said, wet sanding actually works really well on PLA because it keeps the heat down. So if you have that as an option. Otherwise, you can do hand sanding. You just need to go slowly. You can't just do focus on one area. You have to let that heat dissipate. But it'll sand pretty well. And again, wet sanding is really great on it. But you can tumble it in, if you have like a cheap rock tumbler from Harbor Freight, something like that, you can get really smooth parts with that. It'll take most adhesive. Super glue works great on it, but if you need something stronger, epoxies also work. You can also heat weld. So using even a hot glue gun, hot glue would work, or a soldering iron. You can kind of melt two edges of a part or two surfaces of a part and then put them together because it has a relatively low melt temperature. That's easy to do. So there's a lot of ways to bond it. It's pretty easy to work with post-processing. It takes paint really well, and easy to drill into or cut into with an X-Acto knife or anything like that. So you can post-process it really easily.
We've even seen some people use some of those 3D printing pens and actually stitch parts together.
Yep.
If someone's lucky enough to have a dual extrusion material, what compatibility does PLA have with other materials?
So there are a lot of options for PLA depending on what you're looking to do. Of course, that's going to depend a lot on the specifics of the intended purpose of the part, but you can use TPUs and TPEs with PLA. They will bond to each other fairly well. And of course, you can always incorporate mechanical interfaces with them to increase that. Generally, the lower the temperature of the other material, the better. And the reason for that is because of the low heat resistance of PLA. So using something like a carbon fiber filled nylon with PLA is probably not going to work out very well because that will extrude at 260 or 270 C, which is hot enough to cause issues during printing for the PLA. But if the print temperatures are within 20 degrees or 30 degrees of each other, they're probably okay. And then just depends on the specifics of the part. But most flexible filaments, things like PETG and even ABS, you can get them to work together depending on the specifics. But you're not limited. You do have options. And then of course the support materials that work, the PVA, the dissolvable support. There's a breakaway support that works as well. That's very easy to use, prints just as much easier than PVA, and very easy to remove from your part. So that's something I recommend to people if they haven't tried it or are not familiar with it.
We'll kind of wrap up here by using you as a super tech support. You've got more experience problem solving than certainly most everyone within this industry. So what are some watch-outs, common issues that people have, and how would a user solve those?
I'd say with PLA, the most common thing, and this is probably true of most filaments, but if you're not familiar with all the specific splice settings and everything that goes into a print, is changing too many things at once. So generally speaking, the base profiles from almost every printer now are tailored for PLA and are a good idea to start with. And from there, I always recommend changing one thing at a time if you're having issues. That's the biggest one. What often happens is people have a failed print or an issue and they change 5 things and the print's different, but now they don't know what thing they changed.
Or how to revert.
So that's number one, and that's probably for every filament. For PLA specifically, the things that I see happen are I'll call it jamming or clogging issues, and those can be caused by slice settings that are bad, and the things that may cause that would be too much retraction. PLA is pretty much the only filament that's susceptible to what's called heat creep. And what heat creep is, if you're not familiar with it, is essentially materials swell as they heat up or as they get closer to their glass transition temperature. PLA has a low one. So if the temperature near where the filament's melting gets close to that temperature, the filament will swell and cause a jam or a clog in your hot end, where it's not hot enough to melt it, but it was hot enough for it to swell up, and you have issues. That's mostly been taken care of on the hardware side now with better hot ends. E3D and Mosquito and Micro Swiss all have hot ends that are specifically designed, at least in part, to avoid heat creep with PLA, but it still can happen, and too much retraction often is a cause of that. You're retracting molten filament, or not molten filament, but warm filament up into that area and leading to potential swell and a clog. So looking at that, printing too hot is also with there. So yes, you can print PLA at 230 or 240, and often people do for various reasons, but that can increase your risk of heat creep jams. I'd say the other thing I see is people just trying to print too quickly. And there's two things with that. It doesn't allow the PLA to get to the proper temperature before it's extruded. So the symptom I see a lot with that is parts easily delaminate or like kind of crumble. They don't feel very strong. If you can take a part off the bed and break it apart very easily, chances are you were either not hot enough or you were hot, but printing too quickly and not allowing that filament to melt properly on the way out. And tied with that, which is the part of PLA printing that a lot of people experience on the surface quality, a lot of curled edges or curling on corners and overhangs. And that has to do with cooling, and that ties in with speed for a variety of reasons. But, the faster you print, the less time the layer that you're on has to cool when you go to the next layer. So slowing things down can have a pretty significant effect on the surface quality of your part just from that aspect alone without changing anything else, because it allows what you've printed to cool down properly before you put the next layer on top of it. So making sure your retraction settings and your temperature settings are within the recommended range is number one. Making sure that you're not trying to print too fast or print faster than you're able to cool would be number two. Those in terms of most common problems I see with PLA.
And there are some specific designs if you're really interested in calibrating for retraction or print temperatures, print speeds, specific designs that you can find on Matterhackers for tuning those things in individually.
Yes.
Well, thank you for your time, Taylor. Appreciate it. I think we learned a lot.
Anytime.
Now that you understand where PLA comes from, why it's used within 3D printing, and why it's known as a reusable and a kind of a green material relative to a lot of the other options out there, you are ready to get started with 3D printing and succeed with PLA in general. And with that, Matterhackers has you back. So go to matterhackers.com for a bunch of different options in PLA, whether it's our Pro series or our MH Build series. We have getting started guides and how to succeed articles. And we'd love to see what you're making, how you're making it. So please share those on all social media. You can reach out at Matterhackers or myself directly at dgaylord3d. We'd love to engage with you to see what you're making and how you're doing it. Thank you for listening. This has been Dave Gaylord with the Matterhackers podcast. See you next time.